Hello! In this video, we are going to prove the following theorem. Suppose R is a relation from A to B, and S is a relation from B to C. Then the inverse of S compose R is equal to R inverse compose S inverse. Okay, now, to start, if we recall, we know that since R is a relation from A to B, and S is a relation from B to C, from the definition of composition of relations, we can think of B here as our intermediate set, right? That's the way I like to think about it. And we have that S compose R is a relation from A to C. But then, if you recall, when we take the inverse of relation, it swaps the order of these two sets. So really, the inverse of S compose R is a relation from C to A. Right, so just like that. And next, well, since R is a relation from A to B, when we take the inverse of R, it swaps the order of these two sets, and we have that R inverse is a relation from B to A. Similarly, S inverse is a relation from C to B. And now, from composition relations, we can think of B as our intermediate set, and we have that R inverse compose S inverse is a relation from C to A. Okay, now we're trying to prove two sets are equal, so what we're going to do is we're going to prove that everything in this set is also in this set, and everything in this set is also in this set. Let's start by showing that everything in this set is also in this set. To do that, give me an arbitrary element of this set. I'll call it x comma y. And our whole goal now is to show that x comma y is also an element of R inverse compose S inverse. Now, since x comma y is an element of the inverse of a relation, if we recall from the definition of inverse relations, it follows that if we swap the order of x and y, we have that y comma x is an element of S compose R. But now, what does it mean for y comma x to be an element of S compose R? Remember, S compose R is a relation from A to C, where B is our intermediate set. So to say that y comma x is an element of S compose R means that there exists an element in our intermediate set, say B, such that y comma b is an element of R, and b comma x is an element of S. But again, from inverses of relations, if we swap the order of y and b, we have that b comma y is an element of R inverse, and similarly, x comma b is an element of S inverse. And now notice we have that x comma b is an element of S inverse, and b comma y is an element of R inverse. Well, by definition, it follows that x comma y is an element of R inverse compose S inverse. Right? Whenever you encounter a situation like this, you can think of b as their intermediate element. Right? There exists an element b in b such that x comma b is an element of S inverse, and b comma y is an element of R inverse. That's precisely what it means by definition for x comma y to be an element of R inverse compose S inverse. So putting this together, we started with x comma y being an element of S compose R inverse, and from there we proved that x comma y is also an element of R inverse compose S inverse. Since x comma y was arbitrary, that means everything in this set is also in this set. So now that we've shown everything in this set is also in this set, now we're going to show everything in this set is also in this set. To do that, give me an arbitrary element of this set. I'll call it x comma y. We know that R inverse compose S inverse has the intermediate set B. So, what does it mean for x comma y to be an element of this composition? It means that there exists an element B in B, such that x comma b is an element of S inverse, and b comma y is an element of R inverse. But then, from inverses of relations, we know that this is the same thing as if we swap the order of x and b and write that b comma x is an element of S, and similarly, y comma b is an element of R. And from here, it follows by the definition of S compose R that y comma x is an element of S compose R. And again, in this sort of situation, you can think of B as your intermediate element. And again, we know from inverses relations that if we swap the order of y and x, we get that x comma y is an element of S compose R inverse. So putting this together, we started with an arbitrary element x comma y in R inverse compose S inverse, and we show that same element is also an element of S compose R inverse. Since x comma y is arbitrary, this means everything in this set is also in this set. So putting these two facts together, this proves that these two sets are equal. And this is exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.